Going to continue on here talking about a variety of things. So we talked about obviously stoichiometry last time. Again, we did some more limiting reagent type problems. Also, we talked about percent yield, which once again is your actual yield divided by your theoretical yield times 100%. As we talked about, obviously, for percent yield, you are looking for a good high number, is usually pretty much what you're shooting for. As we talked about, not over 100%, but definitely don't want a low number here for percent yield. The actual is, as we talked about in sort of textbook type problems, is typically given to you somewhere in the problem. Obviously, again, if it was a lab situation, it would be actually what you got when you did the experiment. The theoretical is typically calculated. And again, if it's a basic stoichiometry problem, as we talked about, you can follow those 4 sort of steps. If it's a limiting reagent problem, then you can do whichever method you like. But again, somewhere along the way, you do need to determine, obviously, which one's the limiting reagent. The importance of the limiting reagent, as we talked about, is, again, it is the one that really does determine how much product you can make. And when you do that calculation from the equation and what you're starting with, that is what is referred to as the theoretical yield. We then got into solutions after that. I think they're playing a movie. And what movie are they playing? Anybody know? No, that just says come watch a movie. They used to do it all the time. It's like the first movie they played in like 3 years, I think, out there. It's a Halloween movie, so I'm assuming there's going to be screaming. Don't be frightened, I suppose. We should just take our chairs out to the patio and just like watch it, I think, right? That sounds good. All right, maybe later, we'll see. All right, so solutions are really made up of 2 things. It is the solute, which is the smaller part of the solution, and it is the solvent, which is the larger part of the solution. And again, both of those things together really do make up a solution, and the solution is the guys that get the aqueous symbol here. The solute is typically whatever the name of the solution is. So as we talked about, if you have a sodium chloride solution, the solute would be sodium chloride. Most likely in a lot of ionic compounds, water is a very good solvent. It's used a lot. Also polar compounds as well. So that's usually a very good solvent. We started talking about one important unit of concentration, which is molarity. And molarity is abbreviated with a big M. And the big M does stand for technically moles of solute over liters of solution. Most people just use molarity is moles per liter. Again, we do use this sort of formula, if you will, a lot in chemistry, and we do use it to solve for pretty much all 3 things there. So you do need to be able to obviously rearrange it. If you want liters, that would be moles divided by molarity. And if you want moles, like question number 1 on the pre-lab there, you want liters times molarity here. And that's a very, very common way to get moles. We also talked about kind of the importance of sort of getting rid of the big M, especially when you're doing calculations, so that you could see both of the units and stuff like that. So if you had your 3.5 molar sodium chloride solution, it is best to just convert that into 3.5 moles of sodium chloride per liter. So that moles per liter is what the big M stands for. The number always goes with the moles part, and it's always per 1 liter. And really, you can use it like a conversion factor and do dimensional analysis and see the units cancel. I can't tell you how many times I see people leave the big M and frankly, like I said earlier, have really no clue about the liters or where it's at, or even if there are liters or anything like that. So it's really just a visual representation for yourself that you don't miss it when you do it. The other thing we talked about in terms of concentration is sometimes we may be interested in maybe not the concentration of the whole thing, especially if it's an ionic compound. We may actually be interested in the concentration of just the ions that are present. And it kind of works pretty much like stoichiometry. So if we had some magnesium bromide and we had a 0.25 molar solution of magnesium bromide. Because ionic compounds are strong electrolytes, when they're actually in solution, floating around, they really do not stay together. They do break apart into, in this case, a magnesium ion and a couple of bromide ions. So really, if you were to sort of look at the solution, kind of like what we talked about when we did total ionic equation, then ionic equations, you basically have really just these ions floating around. There's none of the magnesium and bromide units still together. So sometimes in sort of molarity, it's helpful, or sometimes you are asked maybe just about the magnesium ion or maybe just about the bromide's ion concentration. And you could do it pretty much like stoichiometry. So if we have this guy, which is 0.25 molar, it is a 1-to-1 relationship between the whole thing and magnesium, which means if you were just interested in the concentration of the magnesium, it would also be 0.25 molar. But when we look at the whole thing here to the bromide, it actually is a 1-to-2 relationship in terms of the bromide ions. So how that affects concentration is we typically would just multiply it by 2, the coefficient there. And I'll try it without my calculator here, but I'm going with 0.5 molar here would be the concentration of the bromide ions in there. So as we talked about before, that's obviously not additive. If you add those together, you don't get the original concentration, but it's sort of proportional wise. Basically, for every 1 unit of this guy that goes for a swim, you get 1 to 2 of these guys. So it's twice as concentrated of the bromide ions floating around as it is the magnesium ions that are floating around. And that's how it's reflected in the concentration. I think I did this last time as well, but this is how we get there in the long version of this calculation, which is you take the molarity and convert it to moles per liter of magnesium bromide. And then you basically just do a stoichiometry here, like we talked about. For 1 mole of magnesium bromide, there are 2 moles of Br minus. Again, the moles of the whole thing cancel, leaves us 0.5 moles per liter of the bromide ion. So that's really the long version of the multiplied by 2 part. So just multiply by 2 could also be very quickly. And that's basically where the 2 comes from. It's the stoichiometry of it. It's the multiple relationship between the whole thing and how it breaks apart. And you can do the same thing for the 1-to-1 relationship. And again, that is how we get that guy's concentration. Works the same way. In the case of magnesium, for every 1 mole of MgBr2, there is 1 mole of magnesium ions. The whole thing cancels. In this case, we're basically multiplying by 1, which is basically what we did here, as opposed to 2, which is what we did here. And that gives us our 0.25 moles per liter of magnesium. Any questions on how to relate molarity to ions by themselves? Now, this is typically usually only used, obviously, for ionic compounds, which are pretty much the only things that make ions when they go in for a swim. Remember, there are molecular compounds that do dissolve, but they don't make ions. So this wouldn't be related. Whatever the concentration of the whole thing that went for a swim would be the concentration of the whole thing as it's swimming around in there. Any questions on any of that stuff we talked about last time there? Okay, so I think we did one example there of molarity. So let's try this one here. What is the mass in grams of Ki that is required to make 500 milliliters of a 2.8 molar solution? Potassium there is 3910. Iodide is a big number, I think. 127, we'll call it, I guess, maybe our 127. I think it's 126. Go 126.9. All right, just take a couple minutes here, and we're looking for how many grams to make this solution that ends up with that molarity there. Okay, let's take a look. So clearly we're dealing with molarity here. And again, molarity is moles per liter. We obviously have the molarity, so we got that guy. We obviously have the volume. It's not in liters, but we can convert it to liters. So if you're not sure what to do, that is like the only thing missing. So that would be probably a pretty good thing to start with. And it does make sense because from that we could get moles, and from moles we could get to grams, right? So we could use our molar mass to do so as our conversion factor here. So we do need to do a little bit of work here. Again, I would take the molarity and convert it into moles per liter of Ki. And in this case, we also need to do a conversion of our volume here, which is 500 milliliters. And again, that is 1,000 milliliters per liter. We're basically going to divide by 1,000 or move the decimal point a few places to the left there. It gives us liters. So we can resolve for this where moles is equal to liters times the molarity. Doing a little bit of dimensional analysis approach, 0.5 liters of Ki. Using our molarity here, and we're going to multiply it 2.8 moles of Ki per liter. The liters will cancel, and that will leave us with moles. And if we do that there, 0.5 times 2.8 gets us 1.4 moles of Ki. Any questions on that setup there? At this point, we now have moles, so it's a conversion factor between moles and grams. So once again, that is our molar mass, right, from the periodic table. That's going to do that for us. In this case, Ki is just one of each of those, so we will add them together, 3910 and 126, 26.9 plus 3910. That's 166 grams per mole, so 1.4 moles of Ki, 166 grams of Ki per mole. Moles will cancel, and that will get us about 232 grams of Ki is needed here. So we would take 232 grams Ki, dissolve it in some water to make a total volume 500 milliliters. And what we should have there is a 2.8 molar solution. Any questions on that? That is like pre-lab question number 1 calculation. Exactly. Yes. So any questions on that there? Okay. Let's take a look at another one here. So why don't you take a moment here, and we want the concentrations of each of the ions in each of the following solutions. So for A, give us concentration of both ions, and for B, give us concentration of both ions in those solutions. At this again, we want to take each one and kind of figure out how it breaks apart in solution. So this, which is soluble, will break apart into a couple of sodium ions and a sulfate ion. That means, once again here, if this is 1.2 molar, it is a 1-to-2 relationship here between the sodium ions and the whole thing, which means we do need to adjust the concentration for the sodium by multiplying it by 2, which means the sodium ions in that solution will have a concentration of 2.4 molar. Now, when we look at the sulfate, it is a 1-to-1 relationship, which means basically we're going to multiply the concentration by 1. And that means that we will end up with the same concentration for the sulfate. Any question on either of those two there? Looking at B, kind of same situation here. We'll take our K2CrO4 in solution. It will break apart since potassium is soluble in everything. That will give us 2 potassium ions and a chromate here. Once again, kind of the same relationship, 0.75 molar. It is a 1-to-2 relationship. So we will multiply this concentration by 2. And I think that gives us 150 there. And between the whole thing and the chromate here, it is again a 1-to-1 relationship. So we would take the concentration and multiply it by 1, which is sort of the short calculation there, and gives us 0.75 molar. Any questions on any of those there? So again, you may be asked in certain cases, like I said, to get the concentration of just the ions, maybe not the whole thing. So you've got to be able to relate the molarity to everybody. Okay, let us then talk about another sort of aspect of solutions, which is dilutions. So a lot of solutions do come very concentrated. So a very common sort of process that we do is the process of dilution. And when we do a dilution, pretty much the only thing that happens is we add more solvent. So a lot of times people say we just add more water. Water oftentimes is the solvent, but not in all cases. But basically, you add more solvent to it. And what happens is the moles of the solute before the dilution will equal the moles of the solute after the dilution. And that is basically because, again, molarity is moles of solute per liter of solution. And once again, it is only the solution part that is the solute plus the solvent. So when we do a dilution and the only thing that we add is solvent, really the only thing that changes with molarity is the bottom number here. It gets larger. And if the bottom number there gets larger, what happens to molarity? It gets smaller. Yeah. So when we do a dilution, we basically add more solvent. It lowers the concentration. Again, kind of like a beverage, right? You get with ice before you come to class, right? It tastes nice and good. And then after class, right, it's been sitting in the sun, all the ice melts and is obviously diluted down your soda there. It doesn't taste as good, right? You try it, but maybe you regret it afterwards. So there is a dilution equation, and it is sometimes referred to as M1V1 is equal to M2V2. This is a dilution equation. M1 is the molarity before the dilution. V1 is the volume before the dilution. M2 is the molarity after you dilute it. And V2 is your final volume of your diluted solution. It doesn't really matter. You can do it either way. In this particular format, as we talked about maybe earlier or last time, this is the one place where, it is okay if you want to leave the volume in milliliters here. And as long as the other volume's in milliliters, it will work out okay. You can still convert it to liters, both of them. But this is one formula that will work out okay because you basically have two volumes and two molarities. So if you leave it in milliliters, you'll get millimoles, but you'll divide by milliliters and it'll come back to molarity. Now, remember though, that if you use just volume and molarity by itself, not in the dilution equation, it needs to be in liters for sure, because you're probably looking for moles. So you definitely need to be in liters. But here, if you want to leave it in milliliters, you can. This is sometimes abbreviated just more generically, like C1V1 equals C2V2, where C here is concentration. So although molarity is the most common unit of concentration and the one we use the most, you technically don't have to use molarity as concentration. You can use some other type of concentration like percent mass or percent volumes on each side, as long as they're the same sort of concentration unit on each side. But most people go with M1V1 equals M2V2 because most of the time our solutions are in molarity. So that's the most common sort of one that we use. But technically speaking, it does not necessarily have to be molarity on both sides. It just needs to be the same sort of concentration unit on both sides. All right, so why don't we try this one? How would you prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock solution that is 4 molar? So take a couple minutes here and figure it out. Okay, so in this case, we want to make this nitric acid solution that has a concentration of 0.2 molar. We want to go from a more concentrated solution that has a concentration of 4 molar. So basically, we have a bottle sitting there that is 4 molar nitric acid. And we want to make a new bottle here, basically, our container that has 60 milliliters, and end up with a molarity of 0.2 molar nitric acid. So we could definitely use our dilution equation here. M1V1 is equal to M2V2. In this case, M1 is typically the more concentrated. It doesn't really matter as long as you keep kind of the numbers together. So we'll go with that. So that is 4 molar. V1 we don't have. M2 is what we're trying to make, which is 0.2 molar. And here our V2 would be 60 milliliters. Again, if you wanted to, you can convert it to liters, but in this case, it will work out okay. When we solve for V1, we will end up with 0.2 molar times 60 milliliters divided by 4 molar. Our molarities cancel. So because we left it in milliliters, our answer will be in milliliters in this case. And that gets us 0.2 times 60 divided by 4. Gives us 3 milliliters of nitric acid here. So that number represents basically how much of the more concentrated guy we're going to take out and basically put into this new container here, which would be 3 milliliters. Now, do I top it off there with 60 milliliters of water? I do not, because if I topped it off at 60 milliliters of water, my total volume would then be 63, right? Which means my molarity would be incorrect. So very common dilution problems. They oftentimes are interested in how much water you need to put in there or something like that. So typically the volume of water is usually your final volume minus your initial volume, which in this case is usually V2 minus V1. So in this one, it would be V2, which is 60 milliliters minus our 3 milliliters, which means I need to put in there 57 milliliters of water. So I take my 3 milliliters of nitric acid, I dump in there my 57 milliliters of water, giving me a grand total of 60 milliliters. I give it a mixy, shaky carefully. All right. And I now should have a solution, right, that has a concentration of 0.2 molar in this case. Any questions on that there? So typically speaking, if you solve for M1, that's usually, again, the concentration of the more concentrated solution. V1 is usually the volume that you need to use of the more concentrated solution. M2 obviously is your more dilute volume, and V2 is your final volume of your diluted solution. And again, the difference between the two volumes is typically the amount of solvent or water that you need to add to get you there. Any questions on that there? Okay, so let's try another one here. We have a more concentrated bottle of calcium nitrate, which is 5 molar. And we want to kind of figure out how much to take out to make a new solution here that has a molarity of 0.25 molar and a total volume of 500 milliliters. So once again, this is going to be our M1 V1 equals M2 V2. Just like before there, we have M1, which is our more concentrated. V1 we're looking for again, and this is going to be 0.25 molar. And once again, here I'm going to leave my units here in milliliters. Dividing this to the other side, the molarities will cancel, and it does leave us in milliliters. And I believe we get 25 milliliters here of our calcium nitrate. Yes, here, 0.0. So that means, again, we would take out of this bottle here about 25 milliliters there. Now, to figure out how much water, which is really what it's asking, the volume of water here would be V2 minus V1. Again, our total volume is 500 milliliters. Our stuff that we've already taken out is 25. So that's a 475 milliliters of water would need to be added. And once again, that would give us our total volume that we're shooting for, which is 500 milliliters. And again, a little mix on that should get us a solution that has this concentration. Any questions on that there? Question on dilutions here. I kind of jumped over this picture here, I think. By the way, this is very often how we make a solution like tonight. Yes. This is a volumetric flask, which means expensive, don't break. Yes, also means there's usually just one line. And that line, it represents the volume here. So if this was, say, 100 milliliter volumetric flask, volumetric, typically you take to 2 decimal places when you record it. In this case, we put a little bit of our solid. You might even pre-dissolve your solid sometimes before you go into the flask. Add a little bit of solvent, nowhere near the neck of the flask at the beginning, so you can get this kind of to dissolve. Like I said, sometimes you'll pre-dissolve like today. And once you got it pretty much dissolved, may require you to add a little bit more water as you're dissolving. You then can take it up into the neck here. And you usually want to do something like maybe a wash bottle dropper or something like that, so you do not go over the line, because if you go over the line up here, can you just pour some out to the line? You cannot, because your solid or solute has already dissolved and you're pouring out your solute, which means it will no longer be the correct molarity. So don't do that tonight. Yes. So it's not as long of a night. So be very careful, go slow, try to get the meniscus there at the line. And obviously that's a very common way that we make a solution. Any questions on that there? So, I don't know what's going on, but stop. Thank you. All right, so let's talk a little bit about gravimetrical analysis. Gravimetrical analysis is a very common sort of stoichiometry procedure. And a lot of times we could use this to figure out an unknown substance. We could take, for example, two solutions together. It makes a precipitation reaction here, and a precipitate is formed. And once that precipitate is formed, we could funnel it and filter it out here. And when we filter it, this happens to be vacuum filtration, which sucks it out really quick, as opposed to gravity filtration, where you just take the funnel and let gravity do its thing. Obviously, in this case, the solid, right, will get trapped there on the filter paper. The liquid part here, because obviously there's liquid in there when you go to pour it out, will come through into a collection beaker. You are probably interested in what's on the filter paper, that solid, which is your precipitate. So typically what you would do is obviously let this dry, and you got probably the mass of the filter paper before, and mass of filter paper afterwards would give you the mass of the precipitate that you made. That would be your like actual yield. Yeah, if you actually did this experiment. You could calculate your theoretical yield based on how much solid or liquids that you started with, and you could calculate something like percent yield. This is a prime example of a situation where you could get over 100% yield because you did not let this all dry. Yeah. And again, you would have, as we talked about last time, some moisture in there that you would be collecting as your solid and your precipitate, but it's really water weight. And that would cause you to have over, for example, an 100% yield, which should not be good. So a lot of times, again, you put it in drying oven, let it sit in your drawer until it really, really dries out, and you make sure you got all the water out of there, so that when you do reweight at the end, you can feel confident that the amount that you got was based on the solid. Another very common sort of stoichiometry situation is really a solution stoichiometry situation, which involves titrations, which we will be beginning today. A titration is basically a procedure where you add a solution of known concentration to one that's unknown. So usually you have one solution, either the stuff up in the burette, the stuff in the beaker, that you know everything about, how much you used of it, the molarity of it. And typically you have a solution where you do not know something about it, like the molarity of the solution. So in a titration, we use a burette, which is this guy right here. It's a long glass sort of tube. It has what it's over here, which is known as a stopcock, which is the thing that opens and shuts it. You drip it here into a beaker or a flask, for which you put a indicator in, typically. And you add an indicator to your solution because it gives you a visual representation of when you should stop your titration. And typically we titrate a solution until it reaches what is known as the equivalence point. The equivalence point is when the reaction is complete, and more specifically in the type of titrations that we will be doing, which is acid-base titrations. The equivalence point is the point where the moles of the acid exactly equals the moles of the base. So at the equivalence point, That's pretty much when everything is neutralized, kind of like we talked about acid-base neutralization reactions. You make water at exactly the equivalence point. That is when both of those guys basically equal each other. So whatever acid you added enough base to neutralize it, or if you started with base, you added enough acid basically to neutralize it. We really do stop. Sometimes it's referred to as the end point. The end point of a titration is where you lay up and go, I think I'm done. And if you did a good titration, your end point and equivalence point should be pretty close to each other. If you did a bad titration, they're very far away from each other. So if you do a good titration, those guys should be at the same spot. The indicator actually works over a pH range. Most indicators work over a specific pH range. For example, ours will do this. So we'll turn it pink. It is phenolphthalein. Phenolphthalein. That's an acid-base indicator, popular for years. It actually works over a pH range of like 8.3 to a pH of 10. Around 8.3, it is actually colorless. As you get past 8.3 and heading towards 10, it is a beautiful shade of pink, depending on where you stop as to what color shade of pink you get. So phenolphthalein is actually colorless in acidic solution. It's colorless in neutral solution, but it does turn pink in basic solution. And it's a good indicator for the type of titrations we do, because at the equivalence point in our titrations, it's pretty much going to be kind of basic happening, which means it gives us that visual representation that happens. Now, because it works over this pH range and it's colorless near 8.3-ish, your equivalence point is in that ballpark, which means usually you're yelled at when you do a titration. Make sure you stop when you see the first lightest color of pink that stays. Like so light, I gotta put like a white piece of paper under it and kind of see the pink that's there. And that is because that will put you really close to the equivalence point. Maybe it's just slightly past it, but you'll be really close to the equivalence point. In terms of volume, it will actually be perfect no matter what in that case. Now, if you titrate and you get like super dark pink, which is personally my favorite color, fuchsia, you might have went really past the equivalence point. So the trick here is, and a very common thing that most people say when they do a titration is this, and we will hear it maybe tonight. I just added 1 drop, and it went from like colorless to like super pink. Yeah. Like really, really pink. And I just added 1 drop. How could that happen? It really happens because the indicator works over that pH range. And when you do a titration, and if you take 200B, you'll learn this, but what happens is as you're doing the titration, you're approaching the equivalence point. And let's just say that this is the equivalence point here. And this is like the volume of base that you're adding, like our sodium hydroxide. So as I approach the equivalence point, you typically will see a pretty vertical jump. Let me zoom in on that for you, in case you missed it. You will typically see this very vertical jump in pH as you approach the equivalence point, right? Which means the pH changes a lot, but does the volume change a lot if you go vertical? It does not. Like it does, you typically drop and you are basically in the same spot. So by you doing like 1 drop or 2 drops too many, you could find yourself on this sort of curve way up here, which is going to reflect in your indicator as super dark pink, right? Now, if you're really careful, maybe you find yourself down here, which maybe it's super light pink, yeah? Is there a big difference in the volume between those 2 spots? There's not, which is really the important thing. The reason they yell at you to go really slow and you want the lightest color pink, and if you have a really mean instructor, they'll make you redo it again, is because if you're not careful and you titrate like I used to do, open it up, shut it, and I was like first one out of the room because like you said pink. I really don't know how great I did because my pink here, dark pink, and my dark pink over here is the same pink, yeah? Which means if I'm over here, I'm like close to my equivalence point volume. I am like way far away, yeah? So if you're really careful as you're doing your titration and you're adding your drops, and what you will see as you kind of progress from the start here and working your way to the equivalence point is, you know, the pink will come, it will go, the pink will come, it will go. Every time you drop it, you'll see the pink, it will go away. It'll kind of stay a little bit longer, then go away, kind of stay a little bit longer, then go away. You'll find yourself getting pretty close to the equivalence point. You can feel you're going to get there because there's usually a good jump in pH to the equivalence point, and then a nice jump in pH after the equivalence point. So what you oftentimes might want to do is you can do what is sometimes referred to as adding a half a drop. So you kind of see like, I feel like if I add a drop, it's gonna go way too pink or something like that. Half a drop means you can open up the burette, let a little drop start to form of the base. You can just kind of wash it down with some deionized water and kind of like dilute the drop. And what that would do is sort of mellow out the concentration of what you put in there and allow it to kind of go to the equivalence point without maybe jumping too far past in terms of the pH. So although you should always try to get the lightest color pink when you do these type of titrations so that you feel like you are in the right spot, even if you get dark pink and you've been really careful, in the end for the calculations, all those volumes are pretty much the same spot. So for our purposes, it's really more important that the volumes of your three titrations sort of agree with each other. They're not all over the place when you do them. And you should try to get the kind of the lightest pink, but don't obsess over the lightest pink as you're doing the titrations. Otherwise, you'll run out of sodium hydroxide by day 3. Just keep redoing it and stuff like that. So as long as you were careful, you didn't just open it up, walk away, and come back and turn it off at the end, you know, you should hopefully be in this ballpark over here and not like when I titrated way over here and stuff like that. Any questions on that? So that is the age-old question of what people often say is, geez, I just added one drop and it went like super dark pink on me. By the way, that also means when you have your phenolphthalein, don't add it to your sodium hydroxide that you made because it's going to turn pink. Yes, there's always somebody that accidentally adds it to their big thing of sodium hydroxide and it turns pink. So don't do that. Otherwise, you got to titrate backwards, go from pink to no pink and stuff. All right, so let's talk a little bit about a titration problem, which is really just a solution stoichiometry problem. So if we wanted to know the volume of sodium hydroxide that's required to titrate 25 milliliters of 4.5 molar sulfuric acid, here what we want to do is it's really a stoichiometry problem. The good news is it's the same stuff that we use in the other stoichiometry problems. The only difference really is in the previous problem to get the moles, we use grams and the molar mass to get the moles. So when you're dealing with solutions, the way we get to moles is we use the liters times the molarity. So that's really the only difference. So these still follow the same basic 4 steps for a stoichiometry problem, which is we need an equation. So we'll start with that. That is sulfuric acid, which is an acid, going to react with sodium hydroxide, which is a base. And when you make a acid and a base, you get salt and water, right? So water is going to come from the H from the acid and the OH from the base. And this is basically a double displacement reaction. So these two guys are going to switch partners here. So that's going to give us on the back end here a little sodium sulfate, which we want to properly balance there with a 2, right, to get the right formula. At this point, we have all the right formulas. We want to balance the equation like a normal stoichiometry problem, which requires a 2 there. And I believe it requires a 2 there to balance it. So it's just like a normal stoichiometry problem. We got to start with the balanced equation. And just like normal stoichiometry problem, we want to evaluate whether or not we got like a limiting reagent situation occurring. So if we take a look here for our sodium hydroxide, we are given 1.42 molar, and we want to know what is the volume basically. For our sulfuric acid here, we are given 4.5 molar, and we have 25 milliliters. So first off, is this a limiting reagent problem? It is not a limiting reagent problem because we cannot get to moles for this guy, right? We only have the molarity, no way to get to moles. So this is a basic stoichiometry problem. We can get to moles with this guy, right? Which is good. And if we think about the sodium hydroxide, we have the molarity, which is moles per liter. So we have the molarity. We are looking for the volume. So the one thing that we're missing is the moles for the sodium hydroxide to allow us to do that. And that is where the stoichiometry part comes in. So we're just going to kind of do our normal stuff here, which is second step, convert to moles. And again, this is where the main difference is. Instead of grams of molar mass, we're going to use the volume and the molarity to do so. That means my volume here needs to be converted to liters. So we're going to divide it by 1,000, which gives us 0.025 liters of H2SO4. Remember that my molarity here is 4.50 moles per liter. So I'm going to use both units there so I can see it. That means I'm going to multiply these two guys like we did earlier. 4.5 moles per liter of H2SO4. That is going to cancel out the liters of H2SO4. And that's going to get us the moles of it, which is in this case 0.1125 moles of H2SO4. Any questions so far? So it's really kind of like a basic stoichiometry problem, balance equation, convert to moles. The next thing is the mole to mole relationship. So in this case, we are given information about this guy, but ultimately we want to get over here to the sodium hydroxide. So we're going to do our mole to mole relationship like we talked about with stoichiometry. And that means that for every 1 mole of sulfuric acid, we have 2 moles of sodium hydroxide. So we'll take our number, which is 0.1125 moles of sulfuric acid. Using the stoichiometry here, we get 2 moles of sodium hydroxide to 1 mole of sulfuric acid. That is the stoichiometry part that's going to allow us to get 2 moles of sodium hydroxide, which, if you remember, is what we need here, right? So that is kind of what we need. So if we do that times 2, going to get us, I'll write it up here a little higher, sorry, 0.225 moles of sodium hydroxide. First off, any questions on that part? So we have moles of sodium hydroxide now. We also have the molarity of sodium hydroxide. So that is going to allow us to get to the volume. So this is the kind of second part of these type of problems, which is a little bit different. Normally in a stoichiometry problem at this point, we take the moles and use molar mass and get some grams or something like that. Here it's very common at the end that we use molarity. Here to find the molarity, use the molarity to get volume or something like that. So the fourth step where we take the moles and convert to some other unit, we still do the same thing and do that up here. So molarity is our moles per liter. In this case, our liters would be moles divided by molarity. Using the moles that we calculated for the sodium hydroxide, which is 0.225 moles of sodium hydroxide, using our molarity of sodium hydroxide that was given to us, we're actually going to divide in this case by the molarity. That's going to be 1.42 moles per liter of sodium hydroxide. That is going to cancel the moles. Let me just clear out some of this here. And if we do that, 0.225 divided by 1.420 gets us 0.158 liters of sodium hydroxide, which is approximately 158 milliliters of sodium hydroxide in this case. So although it may look a little different, it really is the same 4 steps that we use in a basic stoichiometry problem. Balance the equation, convert to moles, mole to mole relationship, and convert those moles into some other unit, in this case using molarity to do so. Any questions on any of those steps there? So it's a very common sort of stoichiometry problem which involves solutions, and that's pretty much what titration problems are. They're really just stoichiometry problems that you use molarity and volume to get the moles rather than grams and molar mass. Any questions on any of that there? Okay, so we're gonna lay it up right there for now.